So to complement the sine rule, which is great when you're working with non-right angled triangles, but of course it doesn't cover every situation. So we also have the cosine rule, which is basically Pythagoras' theorem when you think about it, but it's just applying it to non-right angled triangles. Let's create it. Again, I'm going to drop the perpendicular in, much like I did when we were proving the sine rule. Create two right angled triangles. Now, using Pythagoras, I know h squared would be b squared minus x squared, using the right-hand side. On the left-hand side, the left-hand side, c squared will equal h squared. A here, by the way, is the whole of BC, of course. So the side I want is a minus x all squared. So therefore c squared is equal to, but I'll substitute in for the h squared from above, and we get b squared minus x squared plus a squared minus 2ax plus x squared. The x squareds end up cancelling, so I get b squared plus a squared. So there's the Pythagoras part, c squared equals b squared plus a squared. But then we have this minus 2ax. Well, again, if we have a look at the right side, we can show that, well, look, x over b, that would be the cosine of the angle c. And so x is b cos c. Substitute in, and we get what we recognise to be the cosine rule. So as I say, it's basically Pythagoras' theorem, but it takes into account non-right angled triangles. Because, of course, if it was a right angled triangle, then c would be 90 degrees. And the cosine of 90 is 0. And so it would disappear, and you just get c squared equals b squared plus a squared, which is what we're used to seeing for right angled triangles. But of course I could apply it to any of the sides. So if it was a I was wanting to find, well, again, Pythagoras, a squared equals b squared plus c squared. How do you remember the next bit? Well, it's got to be the included angle between the b and c, because if you think of the right angle triangle, it would be the included angle that's 90 degrees. Another way of thinking about it, if it's the side A I'm trying to find, then it's angle A that I need to refer to. However you remember it, it's up to you. So we could have b squared as a squared plus c squared, etc. And c squared is the one we just proved. Okay, let's do one. So in this case, it would be t squared that I'm trying to find. So t squared will be f squared plus m squared minus 2fm cosine of t. Substitute in. Now, again, be careful with this, because remember, your calculation is t squared, so you need to square root whatever that answer is to come up with t. I've gone to the nearest whole number. By the way, in case you're wondering why I've gone to the nearest whole number, and in other ones I went to one decimal place, if they don't give me an indication, then I'll tend to match the question. So this question, they're all whole numbers, so I thought, I'll round this to the nearest whole number. In another example, I had all the sides were one decimal place. So I went, okay, I'll give mine to one decimal place. The safest thing to do in an exam, I mean, they should tell you in an exam how accurate they want it. But if they don't, what I would do is I'd go t equals, and I'd write the whole calculator answer down, so they can see that, yep, I calculated out correctly. And then on the next line, I go, okay, I'm going to round this off to whatever. Okay, how about if we want to find an angle? Some people like to memorize a different cosine rule for angles. Some people just rearrange the cosine rule. So I'll go that way. It's angle f that I want to find. So again, I'll start with f squared. So f squared is a squared plus s squared minus 2as cos f. And then if I rearrange all that, I get cosine of f. Now, if you do try and memorize in one hit, what do you need to remember? Well, again, the top of the fraction, I guess, there's the Pythagoras' theorem, but you're subtracting the side opposite the angle. So you always subtract, in this case, the f squared. And on the bottom, you get 2 times the other two sides. Substitute in. Again, that calculation doesn't give you f. That calculation gives you the cosine of f. So then you need to go inverse cos, and if you want it to the nearest degree, inverse og. Now, the nice thing about cosine is you do get obtuse angles. So you don't have that problem like you do with the sine rule. It will bring out the obtuse angles straight away. Here's one where the angle we know is not opposite the side we're trying to find. So a lot of people think, oh, hang on, I can't use the cosine rule for this. So I'll go with the sine rule. Oh, hang on, I can't use the sine rule because I've only got one angle. You can use the cosine rule for this. So I set it up, but stick with, well, the angle I know is 25 degrees, so I'm going to pretend like it's A I'm trying to find. So A squared is B squared plus C squared minus 2BC cos A. Substitute what I need, and now it's just a matter of making B the subject. I've actually got a quadratic here. So if I make it look like a quadratic, that's what I have to solve. So, okay, here's a good question for you. What multiplies together to give 40, adds together to give minus 14 cosine 25? Now, if you can come up with numbers for that, you're doing a brilliant job. There's not going to be two nice numbers that obviously do that. So let's go to the quadratic formula. All right, negative b, in this case, 14 cos 25, plus or minus the square root of, well, 14 squared is 196, cos squared 25, minus 4ac, 160 over 2. Of course, it gives me two possibilities for b. Unless they give me more information, I don't know which one it is. So actually, it would be possible to create two different triangles with those dimensions. One where the side length is 5.85, another where the side length is 6.85. Best I can do. So, okay, I've got two possibilities there for the length of B. Let's do a 3D trig problem. Whoop. 2003 HSC. Okay, so David's out there in a life raft. There's his little life raft, cleverly at point D for David. And Anna, at point A for Anna, is in a cabin cruiser. That's a mighty big cabin cruiser, but anyway, is in a cabin cruiser. They're in contact by mobile phone. How fortunate. So David tells Anna, who for some reason has changed the way she spells her name, must be a typo, that he can see Mount Hope. That was lucky. And so David, whilst he's in this little life raft, he just happens to have a clinometer and can go, oh, by the way, I can see Mount Hope, and I can tell its angle of elevation is 16 degrees, and oh, I've got a compass as well. Oh, I know its bearing is 109. Amazing, he's got all that stuff, but he can't find Anna. Anyway, so now Anna goes, well, that's a stroke of luck. I can see Mount Hope as well. And I also happen to have a clinometer and a compass, and she works out her bearing and angle of elevation. And they happen to know that Mount Hope is 1,500 metres above sea level. See, maths in the real world, you've got to love it. I mean, this sort of situation happens all the time. So we want to find the distance and the bearing of the life raft from Anna, so now Anna can go find David. So they can work out all this other stuff, they just can't find each other. Here's our diagram. Okay, let's draw some right-angled triangles. There's the one with David and Mount Hope B. There's one for Anna. And then I'm going to draw the base, because at the end of the day, we're trying to work out David's position from Anna. Well, here's the compass for David. He knows Mount Hope is 109 degrees, so it's that way. And Anna's over there somewhere. Her bearing, well, it's 139 degrees. We're trying to find how far they are and what the bearing would be. So we've got a triangle there. Okay, now the red side is DB. The blue side's AB. I can get that from the two triangles that I drew up. So BD would be 1,500 tan 74. And similar, do a bit of trig, I could show that AB is 1,500 tan 67. So back to our diagram. We now know two sides of the triangle. We want to find the third. How about some angles in there? Well, if I just draw another compass over at B, all those norths, of course, are going to be parallel lines. I should be able to use some geometry here. So NDB plus DBN double dash would be 180. Co-interior angles. From that, I can get angle DBN double dash, 71 degrees. I could go through a similar calculation and work out ABN double dash is 41 degrees. So ABD, again, a bit more geometry, will be DBN minus ABN. So ABD is 30 degrees. So back to our diagram, what have we now got? We've got two sides, we've got an included angle. We should be able to find B using the cosine rule now. So, whoa, look at that. That's a beauty. 1500 squared, tan squared 67, 1500 squared. By the way, notice I don't bother working out what 1500 squared is, because I know I'm going to end up with a common factor of 1500 squared, and I'm going to end up square rooting it anyway. So I don't bother writing down whatever 1500 squared is. It's just a waste of time. Okay, 1500 squared, tan squared 67, 1500 squared, tan squared 74, minus 2 times 1500 tan 67, 1500 tan 74, cos 30. Punch it all into the calculator. Find the square root to the nearest metre, 2,799 metres. Okay, I suppose it's fair enough they can't see each other, so they're almost 3 kilometres apart. So, yeah, fair enough. But they don't have a telescope, they've got a clinometer, they've got a compass, they don't have a telescope. All right, we know how far apart they are. We want to work out that bearing as well. We now have 3 sides of the triangle, we have 1 angle, so I should be able to find either of those other 2 angles now using the sine rule. So I'm going to go for DAB. Sine of DAB over 1574, sine 30. I'm not going to put in 2799 for B because that was an approximation. So whatever that exact value, which is probably still in my calculator, I'll substitute that in for B when I'm punching the buttons. So we'll go 1500 tan 74 sine 30 divided by answer, because that's going to be my last answer. And 2 possibilities. Remember, we're dealing with the sine rule here. Is it possible I could get an obtuse angle? Okay. So 69 degrees 9, or maybe it's 110.51. Now, if it is 69.9, then by the angle sum of a triangle, BDA would have to be 80 degrees 51. But remember, the biggest side is always opposite the biggest angle, things like that. So I know angle DAB has to be bigger than angle BDA. So therefore, BDA must be the 110.51. So it's BDA that I'm trying to find. 100, get a calculator for me. 1500 tan 67, what's that? Let's work out which is actually the biggest side here. 3,533, what's 1500 tan 74? And B was around about 3,000, wasn't it? Okay, well that's okay because 30 degrees. So which one was bigger? The tan 74 one? So therefore, yeah, BAD needs to be the bigger angle. So that's why it needed to be the obtuse angle. Ah, that's what confused me. It's BAD. Let's see, because that's what was confusing me. I had that line there, the DAB was bigger than BDA, so BDA is obtuse. I thought, hang on, that can't be right. Ah, yeah, typo. So that should have been BAD. Oh, I should have known that from this line, shouldn't I? Now, remember this was an HSC question. What would have happened that year is a lot of people would have just assumed the answer was 69 degrees 9. Because, oh, that's what the calculator told me. Got to be the answer. So sometimes you've got to keep an eye out for that. All right, we know it's 110.51. We want the bearing, so I'm going to have to add on the 139 degrees that we already know about. So the final bearing is 249.51. 249.51. Okay, there's our cosine rule.